Mm, Hello, good evening.
Hello, good evening.
Good evening.
Good evening. So today I am little sick. So sorry for that. I'm having little cold.
I think this is the concluding session, I think.
Most likely yes. So officially we
Yeah.
only have 12 weeks. I think there is a possibility that on Tuesday we might have an extra session for 1 or 2 hours, depending on if somebody wants to join.
Okay.
Yeah. So on Tuesday, that is only after 3 days, we might have
What
one more
time?
session. It's in the
What time?
evening. I think that will be notified to you. I think it's in the evening around 6.
Okay.
Yeah.
Although I'm not taking the exam, I'm not giving the exam. So,
Okay.
but Harsul is taking. No?
I think yes.
Yeah, Harsul will.
Yes, sir, yes, sir.
So,
Yeah.
Those are
invite all the
like
best wishes for you, Harsul.
pulse. Thank you, ma'am. Thank you so much.
Where are you actually, Harsul? Where are you from? I mean, if I have the liberty to ask you.
No, I'm from Hyderabad.
Okay.
So
Which university? Hyderabad, which university?
I was a student at Triple IT Hyderabad.
Okay.
Sorry? Which university?
Triple IT Hyderabad.
Triple IT Hyderabad. Okay, that's very nice. Very
Thank
Yes.
you. Thank
nice. That's a very good university, Triple IT.
you.
Okay.
Okay.
We can.
We can wait for a couple of minutes so that
Yeah.
somebody wants to join. It's very unlikely, but let's
Yeah.
wait just couple of minutes.
Manik, do you know Professor Sangeeta
Yes.
Dhananjay Gadre?
Yes,
She
ma'am.
must be a teacher, na? She
Yes.
must be a teacher.
She
Okay.
taught me 3 subjects.
Okay. Actually, I am her husband's a student
Okay.
from Khalsa College.
Yes.
So,
I think she might be about to retire now.
yeah, I think so. Yeah.
Yes.
So which batch are you from? Which batch you passed out?
2020.
Undergraduate. Sorry?
2020.
Okay, 2020. Okay.
Yeah.
The Khas from Karodimal, is it?
Yes. Yes.
Okay, okay. Very nice.
Sorry. So, should we start?
Yes, yes, sure.
Okay. Hmm. So, yeah. So the first problem, and starting with the particle in a box. So I think today most of the problems will be like from throughout the earlier weeks that we had. So it's kind of a mixed set of problems that we'll discuss. Okay, so particle in a box was the very first thing that we studied in this course. So why not start the today's session with one particle in a box problem. Now, okay, we know that this is the wave function for a particle in a one-dimensional box. We have now seen it many times, and we also know that the potential is zero in this range and infinite outside. So all these things we know. And there are 4 statements that are given to us, A, B, C, D, and the question asks which statements are correct and which are not. Okay, so we have to tell which 4 statements are correct. Okay, so do you want to give it a try and
Yeah, I
quickly?
think
Yeah.
A is, looks correct, B
Okay.
also looks correct,
Okay.
and that's it.
Yeah. Yeah. So good. So this is actually the solution. So just quickly let us do it. Why A and B are correct. So we know that this is our wave function psi n x. This is already given to us. Okay. So what is a node? Node is a point where psi is
Nodes.
0, right?
Yeah.
Node is a point where our wave function is 0 except at the boundaries. Okay, so we will not consider boundaries, somewhere in between. So if we start drawing our wave functions, let us draw wave functions. Okay, let's say this is x is equals to 0 and that this is x is equals to a. Now the first wave function psi1 looks something like this, correct? This is psi1. Okay, and how many nodes are there? 0, because only at the boundaries is our wave function going to 0 and there is no other point where it goes to 0. So this corresponds to psi1. For psi2, our wave function looks like this. Yeah, okay. So this is psi2. And here you can see we have one node here in the middle where the wave function is 0. And then we can keep on going like this. So I'll just draw one more. So psi3, it will have two nodes. One here, one here. So if I write number of nodes here, number of nodes, so here it is 2, it is 1 and it is 0. So basically for psi n we have n minus 1 nodes, which is exactly what the first statement is telling us. So first statement is correct. Then the wave functions corresponding to different energy levels are orthogonal. They have to be orthogonal, right? And I'm not going to prove the orthogonality, but you can do that. So to prove the orthogonality, we will take another wave function which we will call psi m of x, which will be same thing. Okay, let's consider these two, and to prove the orthogonality we just need to show that this value psi nx, psi mx, this will be delta mn, right? So that if m and n are equal, they are 1. If they are not equal, then they are 0. Okay, this I think it's already been done multiple times. It's just a simple integration of two sine functions, sine a and sine b, and let's leave it as an exercise. But this we already know that these two wave functions, because they are corresponding to different energy levels, they have to be orthogonal. Okay, then some energy levels are degenerate. This statement is actually wrong, because what is the energy? Our energy of any nth level is given as n square pi square h cut square over 2m a squared, right? And then n goes from 0, so sorry, 1, 2, 3 and so on. So clearly we can see that for each n we have a unique energy, right? There is no such n's, right? We cannot have, let's say, n is equals to 1 and n is equals to 5 giving us the same energy. That is not at all possible. So there is no degeneracy. Okay. And finally, the energy between adjacent levels is a constant. So this we can actually write. So delta E for En plus 1 and En, this will actually come out to be, this factor will come outside, and inside we will have n plus 1 squared minus n squared. So this n squared will just cancel out. Okay, so this will give us pi squared h cut squared upon 2m a squared n squared plus 2n plus 1 minus n squared. So these n squares, they'll cancel out and we'll have 1 2n plus 1 factor. So our delta E, it goes as 2n plus 1, which means that it is not a constant because it depends on n, right? So the energy difference, for example, between the first and second energy level will give us this factor as 3, but let's say between 10th and 11th will give us this factor as 21. So this delta E is changing with n, and therefore the energy difference between adjacent levels is not a constant. So a very quick question, can you tell me a case where this energy between adjacent levels is in fact a constant?
Simple
It's a
harmonic oscillator.
harmonic oscillator.
Correct, simple harmonic oscillator.
Yeah.
Because there, so here energy goes as n squared and their energy goes as n. So if we take the delta, so the n will cancel out and we get just a constant quantity, which is half h cut omega. Okay, so moving on to the next question.
Can I ask a query?
Yes.
If I use a potential well, as a laser, quantum well laser.
Mm-hmm.
So, if I consider one-dimensional case only, so
Yes.
that means in the ground state there will be just one level because there is no degeneracy, and
Yes.
mostly the transition will be from ground to ground.
Mm.
In a quantum well laser,
Mm-hmm.
the transition will be ground state of conduction band and ground state of valence band,
Yes.
semiconductor quantum. So that means, how would I create a population inversion? Even if there is, how many electrons will be there at the at the ground level? There will be just one transition.
Hmm. Okay, so I think what you want to ask is that we have a laser, and for a laser to work we need some delta E, right? And then when this
Hmm.
transition happens, so we get a photon with energy h nu.
Yeah,
Okay, and
yeah,
now you're calling that this is the ground state of your conduction
conduction
band,
band. Yeah,
and this is the ground state of our valence band,
yeah.
right? And to
Hmm.
create a population inversion, we will actually need more electrons here than at the mm,
In
valence
the
band,
valence band.
right?
Yeah.
This is
Uh-huh.
what we have in a population inversion. Okay,
Mhm.
so now what is your question?
The question is, since it's a single level, it is not a band. So in the ground state, there will be the space only for one electron, or maybe two, if we consider spin also. So only one or two electrons can occupy the position of the ground state in the conduction band,
Mm-hmm.
right?
Yeah.
So similarly, in the ground state of valence band.
Mm-hmm.
So how does a laser in this case work?
Okay, so when we call, so there are two things. So one thing that we are saying is that the electrons will follow this exclusion, Pauli's exclusion principle, and we can only
Mhm.
have maximum two electrons in this level, right?
Hmm.
But that is that the things change when we consider a. So this is true only if we have one atom, correct? If we have many atoms, let's say 10 to the 23 order of atoms, then what happens is we know that then we don't have well defined energy levels for the outer shells. Instead they form bands, correct?
No, we are talking of a quantum well. The quantum well, the thickness is only 10 nanometers, say for example.
Okay,
So in 10 nanometer,
then we will have, okay, then basically
we
we are
have
not
just
talking about
levels.
conduction bands, so let's not
Huh.
call them bands. Okay, so let me
In the conduction region, we will have individual eigen values, energy eigenvalues.
just even second.
Similarly, in the valence band,
Yeah, I'll just open a new page and then we can discuss. Okay, Yeah. Hmm. Okay, so then what we have is, let's say we have a potential well like this. Okay, instead
Mm-hmm.
of a band, we have a potential well.
Mm.
And again, we have one more potential well here. And this you are calling has some conduction electrons. And this we have some valence electrons, like some two-level
Mm-hmm.
system. Okay,
Mm-hmm.
so this is like a two-level system.
Mm-hmm.
And here in the ground state, we can only have two electrons, right? These two.
Mm-hmm.
But then for a laser, we will need, one sec, somebody wants to join. Okay. So for a laser, okay, this will work as a laser, right? We can have this transition. We can have one electron going from above and coming down here. Okay, let's say this electron moves down, and this will result in some energy, some photon, which has this frequency given by this delta E. Now, but in reality, we will need many such potential wells, okay, to create this population inversion. Otherwise, you will just have two photons, and I don't know if you will be able to detect two photons, or like what are we trying to do. So then you can model one ensemble kind of a thing, that we have many potential wells here and many potential wells here. And then what the population inversion will mean, that we have more electrons here compared to, let's say, we have a few here. Okay, and because this delta E is same for all of them, so
Mm-hmm.
we'll only get a single frequency, so a monochromatic laser.
Okay.
Okay,
Uh-huh.
okay, so
Okay.
this is how we can model for a like model for a laser using a finite potential will.
Okay.
Okay,
Thank you.
okay, so moving on. Yeah, so yeah, probability current J. So this also we studied long time back. And do we remember how we defined the probability current? So I'll just write it for you. This is the formula which we use. Psi star del psi over del x minus psi del psi star over del x. Okay, this is the probability current, and if you remember, this was useful when we discussed the continuity equation. Okay, now we are given a wave function. You can see it is an exponential iota kind of function, so a sinusoidal function, and a is a normalization constant. Then we are asked to find the probability current J. So for that, let us write our psi, and psi is simply a times exponential iota kx minus et by h cut. Okay, so this will give us del psi over del x as, so this entire thing will remain same, so I can just write psi, and then upon differentiating we'll have one factor of iota k multiplied with it, so iota k times psi. Okay, then if we have psi star, so a remains a, but this iota becomes minus iota, and kx minus et by h cut. So similarly, del psi star over del x, so this entire thing again remains the same, so we'll have psi star and we'll have minus iota k here. Okay, so now all these four we'll plug back in to our first equation, And then we can write our j as h cut over 2m iota, and this becomes psi star iota k psi, and then minus psi minus iota k psi star. Okay, so this thing then becomes h cut upon 2mi. Now this is iota k psi star psi. Okay, iota k psi star psi, and then again plus iota k psi psi star. So then we can write this thing as 2 times iota k mod of psi square. Okay, so we will cancel out these 2 iota, and what we will have is h cut k over m mod psi square. Now what will be the value of this mod psi squared?
A square.
A square. So instead of mod psi squared, we can write a square. And finally, our j becomes h cut k over m times, let me write mod a square. Right, so h cut k over m mod a square, which means option
C.
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 Okay. So next problem, one true or false problem. We are given a wave function which is this like product of 3 sine functions, and we are asked if this is an eigenfunction of Laplacian operator del square. What do you think? Is this statement true or false?
Yeah, I think it is true.
Yes. So if we know what del square is, then it's very easy to see why this will be true. So our del square, the Laplacian, is written like this. Okay. So if we consider
The
just one of the terms, yeah, sorry,
eigenfunction, is it minus 3? Minus, sorry, no, 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 sorry. I just rushed up. Sorry. It will be some addition of k1 square minus k2 square minus k3 square minus
yes,
minus minus.
yes. If these k1, k2, k3 were equal, then we'll get minus 3.
Yeah,
Yeah,
yeah.
yes. Right, so let's say the first term, when we operate the first term on psi, so the sine k1x will, okay, let me write del 2 psi over del x squared will be del 2 over del x squared sine k1x, and then the other two terms, because they are independent of x, will remain same. Right, so a single differentiation of sine will give us cos, so this will become del over del x of cos k1x, but we'll have an additional k1 coming out here, right? And again, so this will be multiplied, the same thing, and upon differentiating again, we'll get minus k1 squared, because derivative of cos is sine, so minus k1 squared, and again we'll get sine k1x, and the same thing here. So this entire thing is nothing but our wave function psi. So it is just minus k1 squared psi. Okay. Similarly, for the other two terms, the partial derivative with respect to y will give us minus k2 squared psi, and the partial derivative with respect to z will give us minus k3 squared psi. So overall, we can write del square psi as a sum of k1 squared, k2 squared, k3 squared multiplied with psi. Okay, so now if we look at this equation, we see that this is an eigenvalue equation, right? So therefore this is the psi is an eigenfunction, and this is the eigenvalue. So this thing minus of this thing is our eigenvalue lambda, and psi is an eigenfunction. Therefore this statement is true. Okay, so moving on. Here we are given that we have a particle moving in one dimension, and it is confined by a double delta function potential. So Vx is such that it is 0 everywhere, and then at x is equals to a and at x is equals to minus a we have a double delta function. So if I had to draw this potential, let's say this is my x-axis. Okay, let's say this is 0, this is our origin. So at x is equals to minus a and at x is equals to plus a, we have these infinite potentials, right? So this function is delta x plus a, and this function is delta x minus a. This value is a, this value is minus a. So this is the form of the potential that is given to us. Oh, sorry, I forgot a g here, and I forgot a g here. Okay.
The option would have mod of x, isn't it?
So these options are little wrong. Here we will have minus a, minus a, minus a, minus a. Yeah, so there was this typo. Now it's fixed. Okay.
Mm-hmm.
Okay.
B. It should be B.
Should be B. Yes.
Although this negative doesn't make any sense because A is just a constant. So minus A is also a constant, isn't it? So main emphasis is on the exponential part rather than the constant. Or maybe if there's an explanation.
Okay, so you are saying option B, right? I think A. No. Okay, we are missing one thing, I think so,
Uh-huh.
because we hurried up a little bit. Okay, so let's read the question once more. So we have defined our potential that it looks like this. So that is great. And here g and small a, they are positive constants. That is all good. And then the question is the general forms of bound state odd wave functions. So the emphasis on odd wave functions.
Okay.
Okay.
Uh-huh. Then it has
So
to be D.
then it has to be D. Correct.
D. Yeah.
So what are odd functions? So if this is my, let's say in general, I'm talking in general, if this is my x axis and this is my y axis, so any function f of x, if it is odd, then basically it is symmetric about the origin. So for example, so this function this is an odd function, fx equals to x. Okay, so like technically the definition of odd function is that f of minus x is equals to minus f of x. So similarly for wave function I can write that psi of minus x will be minus times psi of x. Okay, so if here it is something is positive for x greater than 0, then for x less than 0 it has to be negative. On the other hand, an even function is something like a parabola, like this. Okay, so this is, let's say this is a parabola, so then this is an even function. So for even function, psi of minus x and psi of x both are same, there is no minus sign here. And now this again, like let's say this parabola for example can also be an even function, but for an odd function it must always go through the origin. Okay, so for a general polynomial f of x, if it has to be odd, its general form is something like this. Okay, so this is kind of general form of the polynomial. So you can see if I put f at x is equals to 0, I will get 0 for sure, which means that at origin our wave function is always going to be 0. Okay, so that is one thing that we know. Then other thing that we know is that our wave function must vanish at plus minus infinity, right? So then let me extend this axis slightly. Let's say this is plus infinity and this is minus infinity. So if our wave function is odd, so it must first of all cross through 0 like this, go up, and then again go to 0 like this, and then here again it will go up like this and go to 0 like this. Okay, so this is one of the example of how our odd function look like. Okay, and then the question is for x greater than a, which is this regime, x greater than a, and x less than minus a, which is this regime. Okay, so at x greater than a, we can see that this is more like an exponentially decaying function. So we can write this as a e to the minus kappa x. Okay, and here again it is an exponentially decaying function, but you can see the value is negative, so this will be minus a e to the plus kappa x, right? Because here x is negative. Okay,
Sir, over here, when you drew this diagram and you arrived at these two results, I wasn't able to follow. Could you explain once more?
this left diagram, what I was saying.
No, the right diagram that you drew and how you arrived at the results.
Okay, so let me explain. So this potential profile is clear to you, that we have these two uh, delta potentials at x equal to a and x equal to minus a. Then in the question it is given here that we have to consider odd wave functions. Okay, and then as I explained, for a wave function to be odd, it must pass through the origin. So at x is equals to 0, the wave function has to be 0. It doesn't have any other choice. Okay, mathematically it has to be 0. So then I could mark 3 zeros. So 1 0 being here at the origin, and then we know at infinity our wave function goes to 0, and at minus infinity our wave function goes to 0. Okay, so these are the three wave functions. Now if I draw my axis through this origin, so because it is an odd function, if this has this plus value, positive value in the first quadrant on the right hand side, so for the left hand side it must have negative value, right? So this is what the definition of an odd function is. If for x greater than 0 you have plus 5, then for x less than 0 you'll have minus 5, something like that. Okay, so we have now multiple things. We know that this is 0 at 3 places, okay, and then we also know that this is an odd function, so there is some odd symmetry going on with the wave function. So I just took one example of a wave function with only one node. Okay, I took an example of wave function with only one node and drew how it might look. So it will increase here and hit this well, and then again start to decrease such that it goes to 0, right? Like some exponentially decaying function. So then, which means that for x greater than a, it should have this form. If you look at other options, let's say I pick option A. So for option A, it is given that the form is minus a e to the power kx. Here you can see that if I put x as infinity, that this function will diverge, right? It will not go to 0 because e to the power infinity will give us infinity. So we can straight away eliminate option A and C. And then for option B and D, you can see that they are of the form e to the minus kappa x. Okay. Now only difference in option B and D is that if you look at the second part here, these two terms, the first two terms are same. If you look at for x less than minus a, both have e to the power kappa x, which is good because this term for x to tends to minus infinity will give us 0, right? X tends to, if we put x as minus infinity here, we'll get 0. So this exponential form is correct. Now only thing that we need to decide is, will it be multiplied by a or multiplied by minus a? And we should keep in mind that a is a positive number. Okay. So if we had multiplied it with a, then what we would have got? We would have got a wave function that would have looked like this. Okay. But then our wave function will be even. And the question specifically is about odd wave functions. So to keep our odd function, to keep our wave function as odd, we cannot have a multiplied with, so this quantity will be wrong because this will give us an even wave function. For the wave function to be odd, we must have minus a multiplied with e to the power kappa x. Okay.
And one more thing, sir.
Yes.
I missed how we arrived at this function should be an odd function
No, that is
instead of
actually given. So the question is only about odd wave functions. That we have to assume that the wave function is odd. So if you read the question is the general form of the bound state odd wave functions. Okay, when energy E less than 0 are. So we are talking about the bound states of odd wave functions. So we have to only consider the odd wave functions. Okay. Clear?
yes.
Okay. Yeah. So moving on. Right. So this problem, here we are given a wave function for a spin 1 particle, and the wave function is psi 1 over under root 14, and then it is given in the matrix form 1 2 3 iota. Okay, and this is written in SZ basis. And the question asks the expectation value of Sx. Okay, so the expectation value of Sx. Okay, so for Sx, we know the matrix form h cut by root 2, 0, 1, 0, 1, 0, 1, 0, 1, 0. Okay, so this is the matrix form. And now what is Sx? So we know Sx will be psi times Sx times psi. Okay, so let's first calculate this part, that what happens when we operate Sx on psi. So Sx psi will be h cut by root 2 multiplied by 1 over root 14, and then this matrix multiplied with this matrix. Okay, so h cut by under root 28, and what will this give us? So 0, 2, so this will give us 2, and this will give us 1, 0, 1 plus 3 iota, and then 2. Okay. And now let's do psi Sx psi. So okay, what will, so we have written, okay, this they have given us the ket psi. Now if I have to write the bra psi, what do I need to do? So 1 over root 14 will remain 1 over root 14. Okay, let me bring this down. So tell me, what will this be? 1 over root 14 remains 1 over root 14, and then
And a
what
row
should I write?
vector,
Uh,
a row vector,
row vector
2, 1, 2, minus 3i.
minus 3i. Don't forget to take the complex conjugate. So we'll have minus 3i. Okay, now we have psi, and so this is psi, and we already have calculated Sx of psi. Okay, so we'll have h cut over root 14, root 28, and then just simply multiply this with this. So this should just give a 1 cross 1 matrix, or just a number. And what will that number be? So this will be under root, okay, let me write this as 14 root 2. And here, so we'll have 2 plus 2 multiplied by 1 plus 3 iota, and then minus 6 iota. Okay, so this will just become 2 plus 2, which is 4, and plus 6 iota minus 6 iota will cancel out. Okay, let me just write. So this will become 2 plus 2 plus 6 iota minus 6 iota. So this will cancel out, and we'll only have 4. So this becomes 4 h cut over 14 root 2. And so let me write this as 2, and this is 7, and cancel out root 2 and make this as root 2. So under root 2 h cut over 7. Yes, option B.
Can you please explain this matrix Sx h bar by under root 2, 0, 1, 0, 1, 0, 1, 0, 1, 0? I forgot.
Yes, I have also same question. How this is done?
Okay. So, okay. So first of all, I should note that this wave function psi is given in the sz basis, and that is the conventional thing, right? That we take sz basis and s square basis because both of them commute, and then we write our wave functions in that form. Now, if you remember, we can have the raising and lowering operators, right? So s plus and s minus, and then using s plus and s minus, we can write sx. So this we also did in the last tutorial. Let me just quickly pull that out. Hmm. Yeah, so let me add a new page. Okay, so as I said, we can write our sx in terms of the raising and lowering operators, s plus plus s minus. Okay, and now what this s plus and s minus do? This we wrote in the last class, if you remember, that the function is h cut under root ss plus 1 minus m plus minus 1, and then here we have sm plus minus 1. So this we discussed when we were discussing how to find out the CG coefficients, right? We wrote the s plus and s minus value there. Okay, so for s is equals to 1, this is the spin. It is given to us that the particle is a spin 1 particle, right? Spin 1 particle. So for s is equals to 1, our m can have 3 possible values: 1, 0, minus 1. Correct?
Right.
Yeah. So then, if we have s plus 1 comma 1 state where both s and m is 1, we know that we cannot raise it further. M cannot go beyond 1. So this will be 0. And s plus of 1 comma 0, we know that this will be raised to something like 1 comma 1 and a prefactor which we will get from solving this equation. So if we put s as 1 and m as 0 in this, so what we'll get? So this will be 2, and then minus m is 0, so this is just 0. So we'll get under root 2 h cut. Under root 2 h cut. Okay. Similarly, for the last state, which is 1 minus 1, we again know that it will be of some form 1 comma 0 because we are raising from minus 1 to 0. And then let's put m as minus 1 here. So this is, we know, 2. And when we put m as minus 1, so this minus 1 plus 1, just this, basically this thing. If I put m as minus 1 here, because we are doing s plus, so this is plus, so minus 1 plus 1 is 0, so this term is again 0. And again, I'll just get root 2 h cut as my prefactor. Okay, so this was s plus. Now I can do the same thing for s minus. So s minus 1 1, s minus 1 1 again will give me something of the form 1 comma 0, right? And the prefactor, again, if we put here, you can see if I put m as 1 in the second term, now this time because we are doing s minus, this will be m minus 1. If m is 1, so this term is 0, so again we will simply get under root 2 h cut. Under root 2 h cut. If I have 1 comma 0 here, I know I'll get something of the form 1 comma minus 1. And again, because now m is 0, so this second term straight away goes to 0. I'll just have under root 2 h cut. And finally, for the last term, because minus 1 is the lowest possible value, so I cannot lower it further, so this will be 0. Okay. Now so what is my basis? So these are my, so this will constitute my basis states, and these three that I have written are my basis. Okay. So we know that the matrix element of Sx, so Sx, if I want to write it in terms of the matrix, I have to do this thing, right? And I know I have already defined that my Sx can be written in terms of S plus and S minus. So just half of, so my, let me write again, Sx is half of S plus and S minus. Okay, so now I have okay, so now let me write what will be my state. 1 Sx 0, that will be nothing but half of 1 S plus 0, okay, which is, and now what is this state? 1 of S plus 0. So S plus, okay, so it will raise 0 to 1, and where is this state? Here you can see, here I have this state, S plus acting on 0. So you can see it is giving me 1. So this 1 and this will again give me 1, right? So I'll get some finite number. And what will that finite number be? So Sx acting on 0 will give me under root 2 h cut 1. So this entire thing will just give me half into under root 2 h cut. Now there will be another term, right? 1 s minus 0, and this will just give me 0, right? Because this s minus, when it is acting on 0, I know this will result in a minus 1 state, and this minus 1 and 1 are orthogonal to each other, so this will just give me 0. Okay, so I'll have this thing. So then this just basically gives me h cut by root 2. Okay, so here I did for I is equals to 1. You can see I is equals to 1 and j is 0. Okay, which means the middle state.
Which one state? Sorry, I1 and J0 signifies which state?
So this will be, okay, let me write the matrix here. So I is equals to 1. This is the highest one, right? So we have 1 0, sorry, we have 1 0 minus 1, these three possible values of m.
Mm-hmm.
So this state is 1 1 1, right? This will correspond to 1 comma 1, and
Okay.
this next one will actually correspond to 1 comma 0, and then 1 comma minus 1, and so on. So now here, for example, I'll have 0 comma 1. So this is m values, right? This is not, this 1 comma 1 is not the same as this 1 comma 1, sorry.
Mm-hmm.
So
Right.
this 1 comma 1 is not the same as this 1 comma 1. So here this stands for s, this stands for m, but here these are these I and j values that I am writing, so which are both m values. Okay, so this is the matrix values. So basically, so this the value that I just calculated was this matrix element 1 comma 0, where my kit has 0 as the m value and my bra has 1 as the m value. Okay, that is how I'll construct my matrix. So here you can see that I got h cut by root 2. So I'll take h cut by root 2 outside and I'll get 1 here. Now similarly, I can do for all these matrix elements. Okay.
So ij are m only. I
Yes,
and
yes.
j are m only.
Yes. I and j are m only.
Okay.
Okay. So for example, okay, we can do one more. Let's try to find out what is the first value where both are 1.
Sir, here M means what? ML plus MS.
There is no L here. There is no L. There is
No
no
L.
orbital
That's
angular
what
momentum. There is no
only
L.
S.
Only
Only
S.
S.
Yes, only
Okay,
S.
okay.
Correct. Right. So for the first element where this ij is 1, so what I'll have something of this form, Sx and 1. Okay, and now just simply by looking at it, you can see because my Sx has one term which is S plus and the second term which is I minus. So the plus term acting on 1 will directly give me 0, and S minus acting on state 1 will give me state 0, which is orthogonal to state 1. So this term will be 0. Okay, and by this logic, all diagonal terms will be 0 and only these non-diagonal terms will be non-zero. You can similarly check for other states and you'll also find that these two terms are also 0 and you'll have 1 1 1 for this. So your Sx looks something like this. Okay.
Okay, fine.
Okay. So this is how I have just written Sx, and once we know Sx, it's just some matrix multiplication that we operate Sx on psi, and then we take bra of psi, multiply it here, and then we get our answer, which is the expectation value of S of x. Okay. Any doubts?
No, it's clear.
Yeah, okay, good. So let's take just a break of 2 minutes. I'll have some water and then we'll continue. Meanwhile, if you want to attempt the next problem, please go ahead. Okay, so I'm back. Yeah. So could you solve this one? Yes, no? No? Okay. Okay, so let us begin. Now again we are given so earlier we had a spin 1 particle, right? This time we have a spin half particle. So spin half because S is half, so our M can only have two possible values, plus minus 1 by 2. Therefore, we only have two possible states, and these two possible states corresponding to plus half and minus half, they are denoted generally by plus state and minus state. Okay, so it is given that a spin-off particle is in the state, this thing, then the expectation value of the operation, so the expectation value of the operator iota sx sy will be, right? So one thing, let's write our wave function psi. One thing to note straight away is that our wave function is normalized and the probability of particle existing in the state plus is equal to the probability of the particles existing in the minus state, right? So both the probabilities are same. Now what is this quantity iota sx xy? So for a spin half particle where we only have these two states, we know that we can write our sx as h cut by 2 sigma x and sy as h cut by 2 sigma y, where these sigma are Pauli matrices. Okay, so then this quantity iota sx sy, we can actually write this as iota h cut by 2 sigma x and then h cut by 2 sigma y, or we can write this as iota h cut squared by 4 sigma x sigma y. Now can you tell me what the multiplication of two Pauli matrices will give us? So there is that cyclic relationship between Pauli matrices, right?
Sigma Z.
Sigma
I
z,
can
multiplied with iota.
Okay.
So this thing is nothing but iota times sigma z. Therefore, this entire operator reduces to this constant minus h cut squared by 4 because iota squared is minus 1 and then sigma z. Okay, so and what is the wave function that is given to us? So this is the wave function given to us psi, and to calculate, okay, we are asked to find the expectation value. So the expectation value of this thing will be psi iota sx sy psi, which we know now we can write as minus h cut squared by 4 psi sigma z psi. Okay, so we just have to calculate this function and then multiply it by h cut squared by 4, which will give us the expectation value. So in the matrix form, because I have both these elements plus and minus, in the matrix form my wave function psi I can write as 1 by root 2 1 1. Okay, 1 1. So now what will be my bra of psi? It will be a row vector, and because it only has real numbers, so we'll have just 1 and 1. And we know what our Pauli metric sigma z looks like. So this entire thing psi sigma z psi, it can be written as, so 1 by root 2 1 by root 2 will become half, and here we'll have 1 1, and then here we'll have 1 0 0 minus 1, and here we'll have 1 1. Okay, so this will be half 1 1, and let's do multiplication. So this will give me 1 and 0 0 minus 1, so 1 and minus 1, and this will just simply give me 0. So because this will give me 1 and this will give me minus 1, so 1 minus 1 is 0. So the expectation value that we are looking for is actually 0. Now once we realized okay, once we realized that this operator that we want to calculate the expectation value of is nothing but the like the z Pauli matrix, and we know that this plus and minus are the two eigenstates of the sz operator, right? They are generally, as also discussed in the previous question, that they are generally written in the sz and s square uh, operators space, right? And because we have both states, plus state and minus state, with equal probabilities, and plus state, so sigma z acting on plus state gives us half, and then plus state h cut by 2, not sigma z, sz. Okay, sigma z will just give us something, so sz, so the z component of the spin acting on the plus operator gives us h cut by 2 this thing, and sz acting on minus will give us minus h cut over 2 of this thing. And because both of them have equal probability in the wave function, so this ideally, like this, we could have predicted will be 0, and that is what we get after doing the mathematics. Okay, so any doubt? Okay, good. So
The last part,
One
did
thing,
you explain a
sorry,
shortcut?
sorry.
Did you explain a shortcut for this, the last thing
Yes,
that you
yes,
explained?
right, right. I just told that like both the, like we have equal probability of having an up spin and down spin, and because sz is the eigenfunction of this thing, so sz acting on this will give me plus h cut by 2, and sz acting on the downspin will give me minus h cut by 2, and because both are equally probable, so I will expect a 0 uh, expectation value, right?
But the eigenstates are different, the plus and minus. How can we equate them to zero?
No, because when I have to find the expectation value, so this psi, then I'll have to take the this thing, and then my s of z here, and then again this thing. Okay,
Okay, sir. Okay.
okay. So this first term will give me plus h cut over 2. Second will give me minus h cut over 2, and then taking this on the taking this like the bra of psi, right? I'll just get 0. Agreed?
Yes.
Yeah. Okay. Hmm. Okay, so next question. Here they are saying that consider a system of 5 non-interacting particles. Okay, non-interacting particles with identical spin that are in the same state, half comma half. Okay, confined to move in a one dimension infinite potential of length L. So again, we have a infinite potential one dimensional box of length L. The potential is Vx equal to 0, and then okay, so again particle in a box problem, that inside Vx is 0, outside it is infinity. So this is 0 and this is L. The ground state energy of the system is n times, okay, so they have given ground state energy n times pi squared h cut squared over 2 ml squared, and then they are asking what is the value of n. Okay, so now we have to keep a few things in mind. One thing is that we have 5 particles. Okay, so our total energy will be the sum of all the 5 energies. Okay. Second is that although these particles are non-interacting, but they have identical spins and they are again in the same state, half comma half. So all of them are in the same state. Now what is this half comma half state mean? It means that, okay, so this first half means that it is a spin half particle, like an electron for example, and its ms value is also half, which means that it is in the up state conventionally. Okay, so we can think of it like a problem of 5 electrons and all 5 electrons having up spins. Now if I start to draw the energy levels, let's say that this energy level and then so on. Okay, so let's say this is my ground state. And so on. Now if I want to put these particles in the box, how many particles can I put in the n is equals to 1 state? Tell me.
2s plus 1, which is 2.
2. But in this case, can we do that?
This means
In this case, it is specifically written that all of them are in the same state, which means all of them have off spin, right? So there is no downspin allowed. So ideally, for a single energy state, can we have 2 plus spin electrons? Is this allowed? That I put 2 plus spin electrons here.
Actually, they are non-interacting.
Doesn't matter. Because because then so non-interacting is fine, but because they have spins, right? And
Mhm.
So they have same spin. Means, is
yes,
it possible?
I mean more like a hypothetical problem.
If it
In
is opposite spin, then it is okay.
yeah,
In the same spin,
so this is
how
not
they
allowed,
can
right?
exist?
This is not allowed. This is allowed. Yeah. Now this is not allowed. Why? Because Pauli's exclusion principle. And what the Pauli's exclusion principle is that any two fermions they cannot have same set of quantum numbers, right? So here both these electrons 1 and 2 they have exactly same set of quantum numbers, right? What are the two quantum numbers here? One is n, which defines where in these energy levels our electron is, and the second quantum number is ms. Okay, for this first case both n and ms are same, so this will not be allowed. This, but if ms could have been minus half here, then this would have been allowed. Now the question restricts that we can never have a downspin, right? It is specified that all the particles are in the same state, half comma half, which means all 5 particles have plus half value of ms, right? So ms is plus half for all 5 particles, and then only other quantum number that we can vary to avoid Pauli's exclusion principle will be n. Okay, which means that the filling will look something like this. So one particle here, one particle here, one particle here, one particle here, and one particle here. Okay, do you agree with this?
Yes.
Okay. So now if we have agreed upon this result, now the question becomes very easy. We just have to find the energies of these 5 states, add them up, we have our energy. Okay, so what will our energy be? So every term will have this pi squared h cut squared over 2 ml squared as common. For even, we'll have 1 squared, 2 squared, 3 squared, 4 squared, and 5 squared. Now if we add them up, how much we will get? So I know this is 25 and I know this is also 25. So 50, 54, 55. Therefore, what is the value of n? N is 55. Any doubts in this one? Okay, so for the same problem, if we were not given this information that they are in the same state, that they can take both upspin or downspin, that both are allowed, then the filling would have looked different. So if we had these states and we needed to fill both plus and minus spins, both are allowed, then we would have simply filled it like this. Okay, and then our energy would have been different. Okay, then we will not get 55, we'll get some other thing. Okay, so moving on.
Previous case,
Yes.
if in third energy level there is one electron,
Mm-hmm.
then the energy will be E3. Its energy will be E3
E3,
or
yes.
E3 by 2.
No, E3. So this energy actually, so sorry. So here like we have written no. So this will be, then our energy for this case will be 2 times E1 plus 2 times E2 plus E3, like this.
Okay.
Yeah, like this. Okay, so next question, and here we are given a Hamiltonian. H is something A outer product 1 2 plus A times outer product 2 1. This is the Hamiltonian. And then they are saying for this Hamiltonian, obtain the state vector for t greater than 0. Then the corresponding probability for it to be in state 2 will be. And they are saying take h cut as 1. Okay, so we'll consider h cut as 1 throughout the problem. Okay, now what is this Hamiltonian looking like? So we have 1, outer product 2, and then again we have 2 and outer product 1. Okay, so how will it look like in the matrix form? First of all, it will be a 2 cross 2 matrix, right? Because we only have two states, 1 and 2. So let me define my state 1 as 1 0, and then what will be my state 2? Zero 1. Okay, pretty simple. Now if I take outer product of 1 comma 2, so basically what I am doing is I am doing this thing. So 1 0, and then here I'll have 0 1, right? So this outer product of, so this is outer product 1 2, sorry, Okay, let me write it more properly. Okay, so if I want to write my Hamiltonian, I need to calculate these outer products. So what will be my 1 and 2? This will be 1 0 and 0 1, which will give me, so this will give me 0 1 and 0 0, right? Similarly, 2 1 will give me 0 1 1 0, so this will give me 0 0 1 0. Okay, so finally I should be able to write my Hamiltonian H as, just add these two and multiply by a. So 0 a 0. This is my Hamiltonian. Okay. Okay, so does this look familiar to you? If I take a outside, so this 0 1 1 0, does this form look familiar to you?
This is sigma x.
This is sigma x. So a times sigma x. So this is what my Hamiltonian is. Okay, I don't think the sigma x thing matters, but anyway, we can write this as sigma x. Okay, so now we have written our Hamiltonian. So let's read the question once again. We have to obtain the state vector for t greater than 0. Okay, and then the corresponding probability for it to be in state 2. Okay, so first of all we need to do the time evolution, right? Time evolution of this state vector. So what is our time evolution? So let's say it is u, which is the time evolution operator, and we know that it is e to the minus iota h times t, correct? And I am not
Why?
writing h cut because h cut is 1. Yeah, you are correct, it should be by h cut, but this h cut is 1, so let's just ignore h cut. Okay, now I know I can substitute for my Hamiltonian a sigma x Pauli matrix, and then this becomes this. Now for a Pauli matrix, we have this identity that e to the iota theta n dot sigma is given as I cos theta plus iota n dot sigma sine theta. Okay, which means we can write ut as cos of, instead of theta we have at, and then a identity operator, and then instead of plus iota we have minus iota, n dot sigma is nothing but sigma x, so we have sine at and sigma x. Okay, so if I want to write it in the matrix form, I can simply write this as cos at minus iota sine at, again minus iota sine at and cos at. So this is my time evolution operator. Okay. So now what the question is that obtain the state vector for t greater than 0. So now basically and then we have to assume that the probability for it to be in state 2. So there is some missing information, and therefore we have to make an assumption, like what was its initial state. They have not given the initial state, they have not defined the initial state. So what we'll assume that the particle was in state 1, and then it will evolve in time, and then we'll calculate the probability for it to be in state 2 at some later time t. Okay, ideally they should have mentioned what is the initial state. Anyway, let's assume that the particle was initially in state 1. So then our wave function at time t will be u of t acting on state 1, and our state 1 is simply just 1 0, right? This is our state 1 1 0. So if I do this matrix, same matrix, and put 1 0 here, the u matrix, so what will I get? So I'll get this cos 80, and then this thing goes to 0, and minus sin 80. So I'll get cos 80 and minus iota sine 80, right? Let me add a page. So let me again write my wave function. So it is cos 80 and minus iota sine 80. So now what I can do, I can write this as cos 80 1 0 plus minus iota sine 80 0 1, right? And now this is my 1 state and this is my 2 state. So what I have done is I am able to write my wave function psi of t as cos 80 state 1 minus iota sine 80 state 2. Okay. So this now is my wave function at some time t. Now the question wants us to calculate the probability that this particle is in state 2. So basically we need to find out this probability p2t, and we know that this will be nothing but 2 times psi t and then mod squared, right? So basically what we'll get is, because 1 and 2 are orthogonal, what we'll get is minus iota sine 80 mod squared, and taking the mod we'll just get the sine function, and squaring it we'll get sine squared 80. So this is the probability that we are getting.
Could you scroll up a bit where you wrote psi of t equal to ut into 1?
Yes.
No, slightly above this, the line above it.
Yeah.
The psi t equal to ut into 1, you
Ah.
wrote this.
Yes.
And after that, what did you do? Why did you make the transition from next line? It is after this u2, ut1, u1 to.
So this matrix is basically our U matrix here, right? So I didn't write it explicitly.
This line says psi t equal to cos 80 minus I sin 80 into cos
No,
80
no, this is not
10.
into. This is equals to. Sorry. This is equals to here. So you see, we got this thing, right? That psi t is this. I have rewritten the exact same thing, right? So this psi t is the exact same thing, cos 80 and then minus I sin 80. Now what I'm doing is I'm writing it in terms of 1 and 2. So this is my state vector 1, this is my state vector 2. Right? So if I do cos 80 multiplied with this 1 0, I'll get this term here, and this minus sin 80 multiplied 0 1, I'll get this term here.
Okay, but how is it some standard notation that ket of 1 equal to 1 0, ket of 2 equal to 0 1?
So it's a okay. It is just a two-state system, right? We can only have two states, 1 and 2, right? So we can have 1 and 2, and they have to be orthogonal to each other. Okay. So any operator will be a 2 cross 2 matrix, right? So then let me ask you. Now you can have some other things, right? But what is the simplest possible orthogonal set of vectors that you can define? So for example, we also do this in linear algebra, right? We have our xy plane, that this is x, this is y. Now I want you to give me two orthogonal vectors. Okay. So what is the convention? Like what will you say? Okay, let us take I cap and let us take j cap, right? You know this is going to be true, right? But this is not mandatory. You can take some other vectors also, right? For example, you can take this vector here and this vector here such that they form an angle of 90 degree. Okay, so
Yes,
you can take any set of vectors, but this will make the calculations simplest, right? You can see because one component is 1, other is 0. For the second case, the first is 0 and this is 1. Otherwise we'll have to, and they are also normalized, right? 1 0 and 0 1, so normalized. Yeah, just like the unit vectors I and I cap and j cap. So this is kind of analogous to that, but nobody is stopping you from defining some other unit vectors which are orthogonal to each other, and then you can work using those vectors. That will only make mathematics more complex, but there is no such restrictions. You will again get the same thing, right?
right.
Yeah. Hmm. Yeah. Sorry.
No, sir, no.
Okay.
I'm going.
Okay. Hmm. Okay. So we have till now not done any cylindrical coordinates. So let's see. Uh, let's look at this problem, which is in cylindrical coordinates. So a wave function of a system in cylindrical coordinates is given, that this is psi rho phi z, and this is the form. So this z is the height of this thing, and when this is, so mod of z is less than equal to 1, this is this, and otherwise it is 0. Okay, so then where a is a real positive function, then the most probable value of rho will be
Is it C?
c. Maybe. How did you get it so quick?
Because if you square it
Yeah, it
psi
is.
square,
Mm.
then it will become 2 times rho by A. So that will be A by A. So that will make it unity.
Mm. Can you say that again? Okay,
If
let's
rho is
okay,
okay.
let me write psi square first of all. Okay,
Mm-hmm.
so my psi is a e to the minus rho by a, correct? So then my psi squared will be a squared e to the minus 2 rho by a. Yes. Now please continue.
Yeah, if rho is a by 2, then psi square will be a square into exponential minus 1.
Yes.
So that it will become a constant.
Yeah, okay. Okay. So basically you are correct that when our rho is a by 2, this will be minus 1. So, but our rho can also be, let's say, a by 4, then again it will be constant, right? But what we need to do
Yeah,
actually, we need to look at the form of this wave function, okay? And then the most probable value of rho, uh, I think it's just by coincidence that the logic that you're applying works here. But for the, first of all, okay, we have to find the probability, which is, let's say, capital P. And when we have the probability distribution, let's say this is P, and let's say this is rho, and we'll have some kind of a probability distribution like this, something like this. So the most probable value of rho will be this value where the probability is maximum, right? So this is the maximum probability. So like the mathematical way of doing this thing is finding P and then finding dP by d rho, like taking its derivative and putting that to 0, right? Because here we have a maxima, and this condition will then give us this value, let's say rho most probable. Okay. Okay, so we have already calculated psi squared. So what is our probability P going to be for the cylindrical coordinates P of rho? So we have integration over d phi, which we know goes from 0 to 2 pi, integration over dz, which goes from minus 1 to 1, because that this is given to us, right? That z is confined between 1 and minus 1. Okay, and then we'll have psi squared, which is rho mod psi squared. This additional, there will be this additional rho, right? That will come. Mm. Okay, so upon solving this equation, what we'll have 2 pi, and then this integral over dz will give us 2. So let me directly write 4 pi, and then we'll have rho mod a squared e to the minus 2 rho by a. So this is going to be the probability density, okay, and this will tell us the probability of finding the particle in a radial interval d rho. Okay, so if I multiply this thing by d rho, then this actually gives me the probability of finding the particle. That's why this thing is called probability density. Okay, and then if I next do this integration over all value of rho, which is p rho d rho, I should get 1, right? This will be my total probability, which is the normalization condition. So But anyway, we just need to focus on the probability density and take its derivative such that this dp rho over d rho is 0. So what that means is, so all these constants will be 0, then the derivative of d over d over d rho rho e to the minus 2 rho by a, and this derivative is 0, and then this implies, so first time I can just write rho derivative of the second term, and this will be multiplied by 2 by a, and then just this exponential term. Okay, so this is 0, so I can factor out this term. So this second term basically gives me that this 2 rho by a is 1, or which means that rho is a by 2. So option C.
I think there's a problem in visor in hydrogen atom or some chapter in which we have to find out the position or the or finding the most probable position of finding the electron. So
Yes,
that is also something similar,
very similar.
similar.
That is only in the spherical polar coordinates. That is the only difference.
Yeah, yes. Spherical
Yes,
polar coordinates.
correct. Yeah, you are right.
So then A is the Bohr radius,
Right,
something like that.
exactly. So the most probable value of the radius r you will get as a for the ground state, right? So
Mm-hmm.
and then that is what we define as the first orbit of the electron.
Mm-hmm. Right.
Yeah. Okay. So we still have some time left, and I think this is the last problem. Okay, I have a few more, so let's see how much time we have remaining. Okay, so it's a very simple, like true or false problem, and more like testing the conceptual understanding if we get it right or not. So what do you think? Will this statement be true or will this statement be false?
It will not belong to the same vector space because of the definition of vector space that only the addition and the scalar product.
Mm-hmm.
So this should be in some other vector space. It cannot be the vector in the same vector space. This is what I feel.
But it necessarily not need not be a vector. Okay, so if
Because this will be a higher, it will be matrix, I suppose.
yes,
It will be
so
matrix.
yeah,
The dimensions will change. Yeah.
correct. So this is a vector and this is a vector, and then the question is that they belong to the same vector space, then the outer product is another vector. So that is not true, right? As we have seen for one problem where we had to calculate the Hamiltonian using outer products, we see that this has a kind of a square matrix kind of a form, n cross n, right? So these outer products are generally the operators in that vector space and not a vector, right? So therefore this statement will be false. Okay, but if we have, for example, sorry, psi and then chi, which is another vector in the same space, then what do you think? Is this going to
This
be
will
a
be a
vector?
vector.
This is going to be a vector, right? Because this is like an operator acting on another vector, which we know gives us some vector. Yeah, okay. Or other way to think about it is that this thing we know is like the expectation value, or it will just be a constant,
It's
right?
enough.
Yes. So then we can write it here, and then yeah. Okay, so we still have some time left and we can do one more problem. Let me quickly find out one. Mm, Okay, this is a good problem. So let me quickly write it down for you. So we have a particle at time t is equals to 0. Its wave function psi is given as 1 over root 2 u1 plus u2. Okay, so this is given to us that this is our initial state, and these u1 and u2 are the normalized eigenstates. Okay, so u1, u2, so they are normalized eigenstates with energy, sorry, with eigenvalues e1 and e2, and it is also given to us that e2 is greater than e1. Okay, so the question is, what will be the shortest time after which our wave function psi of t will become orthogonal to psi 0. Okay, so let me again explain the problem. So at time t equal to 0, we are given this wave function and it is existing with equal probabilities, right? Equal probabilities in state u1 and in state u2. And these u1 and u2 are normalized eigenstates with eigenvalues e1 and e2, and e2 has e2 is greater than e1. Now the question is, like, what will be the shortest time after which the time evolved wave function psi of t will become orthogonal to the initial wave function psi of 0. Okay, so because we want to find out psi of t, first of all we have to do the time evolution. So our psi of 0 is u1 plus u2. So what will be our psi of t? It will be 1 over root 2 u1 and multiply with the corresponding eigenvalue. So the exponential minus iota e1 t by h cut plus u2 multiply by its corresponding eigenvalue e2 t by h cut. Okay, so this time h cut is not given as 1, so we'll keep the h cut as it is. And now we have these two wave functions. Now for them to be orthogonal, their inner product must be 0. Yeah, so orthogonality means that this quantity has to be 0. This condition must be satisfied. So what, so if I do this thing, what I'll get? So first of all I'll get
Basically, the phase difference should be pi, isn't it?
yes, Yes. So this will just give me half, right? And so this u1 will give me e to the minus iota e1 t by h cut, and I'll have another term e to the minus iota e2 t by h cut as 0. Okay, so I can get rid of this half, and then what I'll be left with is e to the minus iota e1 t by h cut is equals to minus e to the minus iota e2 t by h cut. Okay, or I can write this thing as, sorry, okay, let me write it like this. Yeah, okay. So then I can bring this one down, and I can write this as minus e1 t by h cut divided by e to the minus iota e2 t by h cut is equals to minus 1. Or I can write e to the iota e to the minus, sorry, I can write e to the iota e2 minus e1 t by h cut is minus 1. Okay, and now for what will be the shortest time t when this will be satisfied. So for that we know that this term, okay, so this first of all we can write this as cos plus sine. Okay, so let me just write down cos of e2 minus e1 t by h cut, and then plus iota sine of e2 minus e1 t by h cut is equals to minus 1. Okay, so because I want a real number on my right hand side, this second term, because this is the imaginary part, this has to go to 0, and this first part has to give me minus 1. Now when is the, like, what will be the smallest value of this argument that will give me minus 1? We know that this is going to be equals to pi, right? So essentially what we will then have is e2 minus e1 t over h cut is pi. Okay, and therefore I can write t as pi h cut over e2 minus e1. So that's it. So what did we do? Just write down our initial wave function psi of 0, write down our time evolved wave function psi of t, write their inner product as 0, and then some mathematics, right? So this thing, and some rearranging. Finally, we get this cos and sine functions. We know that the right hand side does not have any imaginary part, so the second term must be 0, and this first term must be minus 1. So you can see that if we put this thing as pi, the second term automatically becomes 0, right? Because sine of pi is 0 and cos of pi is minus 1. So this choosing pi satisfies both these things. Okay, and then just we get this t pi h cut over e2 minus e1. Any doubts? No? Okay. So yeah, I guess it's more or less time. Yeah. So yeah, we might have one more session as I said on Tuesday, like the final session. I would encourage you to like study well, prepare for your exams, solve some problems. I'll try to solve a few more problems Tuesday if the session happens. And I wish you all the very best for your exams.
Thank you, Manav. It was nice
Okay.
interacting with you throughout the course.
I wish
Yeah.
I was of some help to you.
Yeah, definitely, quite a lot.
Okay, so I'll
So
just
thank you.
also mention my email ID. Sorry, let's take a pen. And in future, do not hesitate to contact me regarding anything that you want. So it's just my name @isc.ac.in, and I'll be happy to interact with you guys whenever you need me. Okay,
Thank
so
you so much.
thank you for being such a wonderful audience, keeping
Thank
the
you, sir.
sessions interacting. That that really means a lot. Okay,
Thank
bye
you.
Thank
bye.
you.
Have a good day
Thank
ahead.
you.
Thank
Yeah,
you. And wishing the students all the best for their exams.
yes.
Yeah. Okay.
Okay,
Thank you. Bye
bye
bye.
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 Thank you, ma'am. Thank you, sir.
Yeah, you're welcome. Bye bye.